All right, hi everyone. This is Dan Barry in Silver Spring, the Climate Program Office. I'm joined in the room by Rick Rosen, Ken Mooney, and Arritt Mariotti. Welcome to the second Modeling Analysis Predictions and Projections Program webinar. The topic of today's webinar is on high-resolution global modeling and regional downscaling and regional modeling. We have three speakers today, Arritt, Julio, Bacmeister, and Stefan, Tulich, and Colle. And the format of the webinar is going to be three 15-minute talks. And for the speakers, I'll give you a 2-minute warning when your time is almost up. We'd like to hold off on questions between the talks and save them to the end of the three talks. We'll have a 15-minute discussion session after the three talks are done. I'd like to remind everyone on the phone line to please mute their lines. And without further ado, I'd like to introduce Arritt, who's going to speak on ensemble downscaling of winter seasonal forecasts. So Ray, I'm going to give the presentation over to you now, and then you can feel free to take it away.
Okay, thanks. Okay, hello everyone. Is my desktop showing up there?
Don't see it yet. Did you click share your desktop?
Yes, I did. Let's see. By clicking it again.
There we go.
Okay. Better now. Well, hello everybody, and thanks to Dan for giving me the opportunity to talk in today's webinar. I'm going to be discussing an application of regional climate modeling that is a little different from what these models have been mainly used for in the past. In particular, I'm going to be talking about downscaling of some seasonal forecasts, which is different from both regional climate modeling over the longer term as well as short-term forecasting, and has some certain challenges that we need to overcome. Just to introduce you to what we're doing, the project that we're involved with is multi-RCM ensemble downscaling of multi-GCM seasonal forecasts, which is quite a mouthful, so we condense it down to MRED, M-R-E-D. This project was originally designed by our colleague John Rhodes, whom many of you know. John unfortunately passed away 10 days before the formal start date of the project, so some of the rest of us had to jump in with coordination and so forth. Formally, we call it MRED. If you know John's sense of humor, often internally we refer to this as Mr. Ed in initials. So, the goal, though, is to test the application of these regional climate models that are usually used for climate scale downscaling to seasonal forecasts. In particular, what we did was to downscale a longish series, 23 years, of winter forecast from the CFS version 1, which ran at T62, about 200 kilometers in horizontal spacing, and downscale that using regional models running at 32-kilometer grid spacing. What we did was downscale not just one CFS forecast, but a full 15-member CFS ensemble for each of those 23 winter years. This gives you an idea of how the ensemble was constructed. We start with the NCEP CFS version 1, which then ran 3 pentads of forecasts, that is starting from different forecast dates, which is the way that CFS seasonal forecasts do. This is sometimes called a lag ensemble. Then each of those 15 initial dates ensemble members was downscaled by the full range of the regional climate models that you see here. So we have 15 members of each winter downscaled by an ensemble of regional models. We put those together, and we've got a multi-realization, multi-model ensemble seasonal forecasts. I'm going to show just some preliminary results here in the interest of time. People are wrapping up their reformatting of the data and so forth, and individual groups are moving ahead with their analysis of their own output. We've also got a few preliminary results for all the simulations together as an ensemble. So I'll first mention a few individual results before moving on to the ensemble. Here's an example from one model, in this case, the ADA FSIB model running at 32-kilometer grid spacing. This is being done by Yongkang Shu's team at UCLA. And when he compiles statistics for the CFS versus the downscaled results for the entire United States, we see a reduction in both the bias, cutting it roughly from 1.52 millimeters per day down to something very close to zero, and a corresponding reduction in the root mean square error over the domain, along with an increase in the spatial correlation. So we're seeing that, at least from one model, there is an improvement in the domain-wide statistics for precipitation. We move now to a specific event. This is a single model MM5, which we're running at Iowa State University. What I'm showing here is the precipitation during the strong 1997-98 El Nino event, in particular the mean precipitation rate for the months of January through March. And what we can see here is that the global model produces a precipitation anomaly, that is a difference from its own climatology, roughly in the right place in the western U.S. here, which compares to the observed location of the western U.S. here, but in a much more spatially diffuse way. Then also a precipitation anomaly over the southeastern U.S., which compares to, again, this more structured observed anomaly over the southeastern U.S. When we downscale the CFS results with a particular regional model, in this case MM5, what we're seeing is now a precipitation anomaly that is similar in overall nature to what the CFS has, but is more closely tied to the terrain, as we see in the observations here. So what we're doing is taking a broad scale global model result, then providing detail, in this case, locked mainly to the terrain. In other words, we're doing true downscaling. We're not just actually replacing the global model with the regional model. If we look at a few statistics now in terms of the size of the ensemble, what we're seeing is that both the CFS and, in this case, the ADA model, again, benefit from increased ensemble size. There's perhaps some indication that the regional model benefits a little bit more from increased ensemble size compared with the global model, and that the cost-benefit ratio, if you will, for increasing numbers of ensemble members versus decreasing seems to level out somewhere around 5 or 6 members, which has some implications I'll mention later on. Masao Kanemitsu, shortly before his death, and Laurel Jahan came up with an interesting method to try to get at this perennial question of the added value of regional model simulations over the global model by providing what they call a value-added index, which looks at the PDF of the skill over some region above a cutoff, which is our minimum useful skill or critical skill here. Looking at this range, we look for a crossover point where the regional model skill exceeds the global model skill, and then the added value index is then represented as essentially, the area over this domain in which the regional model provides improvement over the global model. If this crossover point doesn't exist, then the value-added index is 0. That is, there's no place in the domain where the regional model provides better skill than the global model. So this is just one more tool to add to our arsenal in trying to find out this overall question of the added value from downscaling. Turning now to the ensemble results, a point that I can't emphasize too strongly is that the regional model skill ultimately depends on the skill of the driving global model, in this case the NCEP CFS. So what I'd like to show you very quickly is where the global model has skill. And it's no surprise, of course, that that is primarily in the places where we have a strong ENSO signal, the southwestern United States and the southeastern United States. So keep that in mind as we go through some of the regional model results. Here I have some statistics for the mean precipitation over a region in the southwestern U.S. every year for both the CFS global model and the regional models, as well as comparison to a couple of observational data sets here. It's hard to pick out the global model amongst these curves, and that's really sort of the point. The point being that the regional models in an area average sense tend to track along with the global models, but provide more spatial detail. Again, if we look at the cases where there's skill, we see that the strong El Nino events in 82, 83, and 97, 98 are fairly well captured by the ensemble mean of the regional models. But there are places where the global model, which just happens to be this purplish curve here, does something that it shouldn't, like in the winter of 91, 92, and the regional models just follow it along. So a really important point is that the regional models can't take a gross error in the global model and somehow correct it. If we look now at a comparison of temporal correlations in this case for 2-meter temperature and precipitation, we see that for the multi-regional model for 2-meter temperature, there is a large area of improvement. Unfortunately, this is in a region where the skill of the global model is very low. So even though the regional models have improved upon the global model here, the skill is still not brought up to a useful level. So just because the regional model is improving on the global model still doesn't necessarily mean that we have useful skill overall. If we move now to precipitation, we see in these warmer colors, the yellows, oranges, and so forth, that there are fairly large areas in the central and western U.S. where the downscaled ensemble gives a substantial skill improvement over the global model, and we have useful skill. So we seem to be doing better for precipitation, at least in the wintertime, than we do for temperature. I'm going to show now some results that were obtained by Ruby Lung and her group out at PNL. She applied 2 statistical methods to both the global model and the regional models individually, as well as in an ensemble. The first is bias correction and spatial disaggregation, which essentially corrects the PDF based on long-term observations. And the second one is a Bayesian merging technique. And these give somewhat different results. If we look first at precipitation, the root mean square error of the precipitation anomaly shows that the bias-corrected and spatial disaggregation method produces, by a small margin, the best results at a 1-month lead. Throughout the 5-month lead, then the Bayesian method applied to the CFS is competitive with the Bayesian method applied to the multi-model downscaled ensemble. Turning now to temperature, we see a roughly similar result in that the bias-corrected and spatial disaggregation method applied to the downscaled ensemble produces the best results at a 1-month lead. At the 5-month lead, things look different. And again, the Bayesian method applied to the global model produces the best results overall, comparable essentially to the Bayesian method applied to the 6-RCM ensemble. Something that we see again here is something that we've also seen in climate type simulations, which is there's no single best or worst regional model. If we look at the best and worst performers for temperature and precipitation, we see that they flip-flop quite a bit. So what does all this mean? Well, we're still figuring out, but we do have some preliminary conclusions that we can share. The first is, once again, to reemphasize this point that the regional models truly are downscaling. That is, they take the global model and they provide more spatial detail. They don't take a grossly erroneous result like we saw in that case for 1991-92 and somehow correct it. The second point is that the added value from downscaling varies a lot. It varies with the region. It tends to be better in the case we've looked at for the western U.S. and central U.S. than for the eastern U.S. It varies with variable, tends to be better for precipitation, and it varies with the large-scale environment, in particular with the strong ENSO events providing both our best improvement and our best overall. Statistical post-processing helps to extract value from these downscaled forecasts. That is, we shouldn't look at statistical and dynamical methods necessarily as competitors, but we can use the two of those together to try to obtain the most value out of the downscaled results as well as the global results. And then finally, just to reiterate, the downscaled results ultimately are tied to the global model, so that improved global model forecasts should give us better downscaled forecasts as well. The better input we have to the regional models, the better output that we'll get in the end in terms of downscaling. And then finally, where do we go from here? I think that probably the most useful extension of this work would be to apply it to seasonal forecasts for multiple GCMs. As we've seen, the downscaled results depend critically on the fidelity of the GCM itself, so that if we can apply this to a multi-GCM approach where we have multiple regional models downscaling multiple global models, there's a lot of reason to expect that we could have very substantial improvements in our skill. A specific hypothesis out of this is that if we do, say, 15 simulations, it may be a better use of our computer time and human efforts in doing the downscaling to downscale, say, 5 members from each of 3 global models, 15 members from a single global model. That would give us a better ensemble overall. There's evidence for that in some of the results that I showed, that the benefits started to flatten out at around 5 or 6 ensemble members. And that concludes my presentation.
Great. Thanks a lot for your presentation. That was excellent, very interesting. I'd like to remind everybody on the line to write down your question if you have a question specific to Ray's talk, and we'll have a discussion session after all 3 speakers have finished their presentations. So right now I'm going to switch it over to Brian. So Brian, I'm throwing over control to your computer.
Okay. Okay. Can everyone see the presentation?
Yeah, it looks great.
Okay.
Thanks. You can go ahead.
First, let me say that I'm fighting a head cold here, so if I sound like terrible, it's not your speaker or phone. It's actually my voice. So I'm going to fight my way through this here and give an overview of a project that we actually just started at Stony Brook a couple months ago, looking at high-impact weather along the East Coast, basically East Coast winter storms. And there's this is a collaboration between myself, who's done a lot of mesoscale modeling over the years, and Minghua Zhang and Edmund Cheng, who does storm tracks, and then some students and a postdoc here. So as the picture illustrates, this is New York City, and I don't probably need to convince everyone how these winter storms can have such a large impact. And this is the record snowfall from a few years ago with over 2 feet of snow. And so the impacts are obviously widespread up and down the East Coast, but during these winter storms there's obviously a lot of mesoscale or small scale impacts, and just sticking with the theme of this picture here, one of the major impacts are these snow bands, for example. So within these extratropical cyclones, there's a lot of important mesoscale structures that, when we're thinking about regional climate change and so forth, extreme winds, heavy snowfall, we need to keep track of some of these things. So, and this figure here shows in the upper left is a radar shot of one of these snow bands across Long Island, and what I have here are just some simulations using the WRF model at different resolutions. And so you can, as you could imagine, at 180 kilometer grid spacing, you're not going to resolve much. The cyclone is way too weak. So obviously we need to get down to less than 60, and then even at 20 kilometer grid spacing here in the lower right, you can see some structures are getting a little bit more realistic, and the surface pressure is now closer to what was observed in this case. So basically the motivation, there's obviously a societal impact motivation here that I've already outlined. But basically, there haven't been many dynamically downscaled studies of mid-latitude cyclones along the east coast of North America in the western Atlantic. So we wanted to tackle this problem here using an ensemble of moderate resolution WRF runs, basically nested within a climate model ensemble, and then see if we can actually calibrate that ensemble to actually think about the future predictions of these mid-latitude cyclones. There's other factors too that we want to investigate. Obviously, the sea surface temperature, the resolution of the SST is going to be important, and you can imagine other land surface, snow cover characteristics will be important as well. So I'm just going to outline the basic approach, and then I'm going to show some preliminary results here. I'm not going to have time to go into the details of our approach, but just to outline it here. Obviously, there's a lot of uncertainty, so this is going to be an ensemble approach where we're going to couple initially in a one-way configuration the CCSM with WRF, and start with a training period from 1984 to 2004. In which we're going to vary some physics, the sea surface temperature, land surface models, and I'll highlight a little bit of that here in a second. We're also going to run this ensemble with the NCEP2 analysis. We're already starting that process, and the idea is to basically, once again, get this training data set to verify the cyclones in our WRF simulations. And the whole idea is basically to use these historical runs to bias correct and weight these members. And we're going to use a similar approach to what Ray mentioned, usually a PDF approach or a cumulative distribution function adjustment to try to bias correct. And then we're also going to calibrate the ensemble using Bayesian approaches as well to try to get a more calibrated ensemble. And then the idea is that basically, given those weights and calibration, when we run our future runs, we can hopefully get a more realistic result in terms of the calibrated cyclone density tracks, extreme temperatures, and so forth attached to these cyclones. Okay, so our setup, as we currently have it, we're testing some things right now, but we've been running a 20-kilometer WRF over this 20-year period. Starting with the NCEP2 analysis, and the upper left is actually the domain that we're running here with the WRF at 20-kilometer grid spacing, and have just picked a random cyclone event here on the East Coast. And then on the lower right is actually the corresponding NCEP2 reanalysis. So obviously you wouldn't expect perfect matching since we're driving from the boundaries, and this has been running for about a month or two. I mean, we started the season at October 1st, and now we're looking at November 5th, basically, for this given season. But I'll show you here in a few minutes that even getting the distribution of these cyclones is maybe a challenging aspect for these RCMs and so forth, and I'll mention that here in a few minutes. So our ensemble here, we're going to try a few things. This is a nasty-looking table with a lot of characters. I apologize, but there was an interesting study by Lawrence Livermore looking at the global models and the sensitivity of various parameters, and so we're going to use this as a starting point for our physics perturbations for our GCM within the global model. So you can see they're ranked here from 1 down to 20 or so, and so we're going to, especially the top half of this is going to be used to create basically 8 to 12 CCSM members of the ensemble. And each one of those CCSM members will drive a particular WRF member, and I have a table down here of 8 representative members in which we're going to add a lot of physics diversity here to the WRF members, which are run at 20-kilometer grid spacing. So that's our plan here to create our basically 8 to 12 member ensemble before we to do that training data set. So obviously that's a lot of number crunching, and things are running right now as we speak. But while we're basically waiting for some of those simulations and results, what we have been doing, what I wanted to share with you is some other preliminary results using the NARCAP data. And I think everyone's familiar with that, where these regional models are run at 50-kilometer grid spacing or so, and the domains are shown in all these boxes. What we're interested in, I mean, one issue with using the NARCAP is obviously it doesn't go as far off the coast as maybe we would like, but we are interested in this boxed region. That's going to be our East Coast winter storm region of interest. And what we've done is grid all the NARCAP members onto this blue area, basically the smallest domain, and that's going to be a common grid on a 0.5 degree resolution grid, so getting it all onto a lat-long grid effectively. We're in the process of getting all the NARCAP members, and I'm going to show you some preliminary results in the red here, where the Canadian Regional Climate Model and then the WRF using the GREL parameterization either driven by NCEP here or the CCSM and so forth. So this obviously is a useful data set to start thinking about what's going on with these RCMs and these cyclones. But we do need a tool, and one thing we've done in the last month or so is implement a cyclone tracking procedure, a program developed originally by Hodges to track these cyclones. And I just want to spend a few minutes describing this, but basically the whole idea is basically to bandpass filter the mean sea level pressure field. You can also track 850 millibar vorticity fields, but we've settled on the mean sea level pressure since we're simply looking over the eastern U.S. and the Atlantic. And it uses a discrete cosine transform for this spectral decomposition over this limited area domain of the RCM. And the idea is that we want to remove the planetary scale wave numbers less than 5, and also the somewhat smaller scale waves greater than 42 here. So the way it works, basically, first, in a very simple way, is something called segmentation, where it identifies the objects around a minimum sea level pressure field, and those objects are stored for tracking. And basically, to track, it's using a cost function minimization approach, where it's basically estimating the next potential cyclone position, and then searching around and finding that position downstream, and that cyclone will be identified and tracked, and then given a unique storm ID here. So we play with a lot of parameters, and I'll show you some verification of this tracker here in a second. Obviously, there's uncertainty with this as well, but we've settled with wavelengths between 600 and 10,000 kilometers here to concentrate on the synoptic scales. And we're requiring the cyclones to have a minimum lifetime of 1 day. We don't want any short-lived spurious events, and we also want these cyclones to be moving and not a thermal low or something attached to the terrain. So we have a minimum moving distance of 1,000 kilometers or so. So here's just an example of a case here where on the left is a sea level pressure field from, I think it's the CFSR reanalysis. And then the filtered sea level pressure is in the middle here, and you can see after going through the filtering, it's identifying these blue areas, which are the cyclone minimum. And then you can see the corresponding dot, the cyclone centers, which this is a 6-hour sequence, which can be connected here to create our cyclone track. So what we want to do is try this out for the CFSR as well as the reanalysis as well as the NARCAP members, and this is somewhat challenging with the Hodges tracker because it really likes a lat-long grid, and all the RCMs are on different projections. And so rather than modifying the Hodges tracker to deal with all the different projections, what we did is put all the data onto a 0.5 degree grid, and we're interested in this black region shown in the middle. But we did, to run the tracker, we do need a buffer zone where we have data extending to the corner points, where all we did was just extrapolation. Obviously, that's all bogus, and we're going to be throwing that out, and we're only interested in what's inside the domain. But just in order to run the tracker here in the lat-long grid and take advantage of the full RCM grid, we did have to do this outer extrapolation first. So given that, we wanted to do some verification, manual inspection of what's going on, and what I have here is what we did, where we actually tracked manually 600 centers over about 10 Januaries every other year from 1979 to 1998. And you can see the center density here in the color shading here. And what we're interested in is this blue boxed region. And what we did tracking manually is to see how well the tracker was doing compared to the manual inspection. And the good news is it's basically within 5 or 10% in terms of missed centers and false alarms. So there's going to be an uncertainty bar. Some years might be larger than this, but I think we're capturing most of the cyclone events here with this tracking approach. And so forth. And notice I'm leaving there's going to be a buffer period between our area of interest and the outer domain because obviously with the boundary concerns and extrapolation, we can't believe the results right near the boundary. So that's where the blue box is, about a few hundred kilometers west of there. Okay, so we have we have been looking at these NARCAP members, and just to look at the cyclone density here for DJF over about a 20-year period from 79 to 1998, where we're looking at basically the number of cyclones per 2.5 degrees latitude longitude for each winter season. So we're looking at the number per winter here. And the CFSR analysis is here on the left, and you can see nicely the storm track here off the East Coast showing up in the reanalysis, as well as the maximum near the Great Lakes. And then what we have on the right two panels are the WRF and the CRCM driven by NCEP. And you can see quite clearly here that there's a reduction here in the density of cyclones in these two NARCAP members. So basically, what this suggests is that the RCMs are not predicting enough cyclogenesis or cyclones here in this Western Atlantic or East Coast domain. And what we have taken a look at this in the last few weeks. And what we found, and this is just a representative case, I could show you 4 or 5 other interesting cases where this is an event from 1986, which was a particularly bad year for these 2 NARCAP members. But I'm just showing you sea level pressure, the NCEP2 analysis, and as you would expect in the western part of the domain, the RCMs match the analysis fairly well because they're driven with the boundary conditions and so forth. But you can see by the time we get to the central U.S. and eastern U.S. here, for this case, the anticyclone is much weaker in the RCMs, and there's a lack of East Coast cyclogenesis here, driven by the NCEP boundary conditions. So there's some interesting things going on here and potential biases related to thinking about the capability of the RCM in generating a probability or a PDF of cyclogenesis along the East Coast, and that's motivating, obviously, why we want to do our own ensemble to also dive into this issue. And needless to say, it's not going to get much better if we just look at the predictions of the RCM driven by the CCSM, and that's what's shown here in the right 2 panels compared to the just as a reference here, the reanalysis, and you can see once again sort of this underprediction of cyclone density here during this 20-year period or so. So just in summary here, we're in the process of running an ensemble here of a one-way nested CCSM and WRF for basically a 20-year period down to 20-kilometer grid spacing. I should mention that I knew I wouldn't have time, but we're also developing a 2-way interactive nesting capability here at Stony Brook. Minghua Zhang is leading that between the CCSM and WRF. So we, in the next year, should have the capability to also test the impact of running a 2-way nest. And there's also a climate WRF being developed, CWRF, that could be a useful ensemble member, too, to also test during this training period. And so the idea is to calibrate and weight the ensembles before we run a similar set of runs for future climate predictions. And we've implemented a cyclone tracker so we can keep track of the cyclones, so it's more of an object-based verification here. And obviously we can keep track of other things within the cyclone as well, heavy precipitation and wind and so forth, that we can also think about tracking. And so the preliminary results is that, and something we're going to have to keep an eye on with our own runs, is just the capability of these models in predicting the appropriate distribution and intensity of these cyclones. And the 2 NARCAP members we've looked at so far are suggesting some underprediction. And with that, I'll close here.
Thanks a lot, Brian. That was an excellent talk. So our final talk for this session. Oh, and thanks for battling through your cold, too. You didn't sound too terrible, so you must be hopped up on a lot of Dayquil or something.
Yeah. Yes.
So our final talk is by Julio Bacmeister. Stefan Tulich is going to give a short intro to the talk. And so Julio and Stefan, I'm throwing the control over to you right now.
Okay. So I do this, sharing this up. Okay. Do you have the desktop?
We do. We see it clearly. Thanks.
Okay, so I'm going to open this this talk, so there's a change in title because it was suggested that I sort of give some background information on this project, and then Julio is going to be talking about some work that he's been doing that feeds into the project. So the project title is Improving Convection Parameterization in the MJO and Next Generation Climate Models. So I'm going to give an overview and then some preliminary work from Julio. And the co-PIs are Julio Bacmeister at NCAR CGD, Bill Putman at NASA, Goddard Space Flight Center, and Ming Zhao at GFDL. And then I'm at CU Series and ESRL here in Boulder. Okay, so running global models at 10 to 20 kilometer grid spacing is now quite feasible, and in the next coming years we're going to be seeing climate projections at these resolutions for 20-year time frames, and these resolutions are of interest because you can start to resolve tropical storms, which is obviously of great concern from the standpoint of predicting climate change. And so I have a picture here of one model that can be run at this sort of resolution. It's called HIRAM, and it's being developed at GFDL. And Ming Zhao is actually working with this model. And this is a slide showing prediction or a simulation of cyclone tracks made by this model in comparison to observed cyclone tracks for the period 1981 to 2005, and you can see it's fairly realistic. So these types of models can do a pretty good job at capturing the climatology of storms. However, if you look at other aspects of these simulations, there's not perfection in all aspects of the model. So on the left here, I'm showing output from a regional WRF simulation of the global tropics that was done with reanalysis driving at the boundaries at 45 south and 45 north in comparison to observations. And so you can see you've got some pretty substantial biases in the mean rainfall with too much rain over the West Pacific and South Pacific. And then if you look at the transients in these types of simulations, you find that they're doing much better than, say, the previous generation of low-resolution models, in that they're capturing certain modes of variability that you want your model to capture. For example, easterly waves and Kelvin waves. But if you look at the low-frequency variability in both this WRF model run that I'm talking about and actually in HIRAM as well, they don't seem to be able to get the MJO. So this peak down here in observations corresponds to the MJO, and if you look at either of these models, neither of them seems to have an MJO peak. And so obviously this is something that you want your model to capture, because the MJO is sort of at this interface between weather and climate. So this is a schematic sort of illustrating this point that the MJO impacts weather over the U.S. on timescales of 15 days, impacts tropical cyclone development, but it also can play a role in climate. So there's been observations showing a linkage between the MJO and, say, ENSO. So from the standpoint of making predictions on intraseasonal timescales out to decadal timescales, you need to have the MJO if you want to have faith in your predictions. And so this missing MJO presumably relates to some deficiencies in physics, and it sort of highlights an issue that is coming up when you talk about high-resolution climate modeling, in that traditional climate model grid boxes with scales of several hundred kilometers, you sort of have a scale separation where your grid box is large in comparison to the size of individual clouds, and so the assumptions that are made in developing parameterizations are more valid in that range. Whereas if you go to these sort of 10 to 20 kilometer resolutions, you're now approaching resolutions where individual clouds are of the same order as the scale of your grid box, and so the assumptions that you're making are breaking down, and so obviously you have to make some adjustments for these new resolutions, and there's uncertainty in how to do this at this point. So the goals of this project are to assess and optimize the performance of, are we okay? Is everyone there?
Yeah, that looks like something on your computer. Okay,
okay.
We're good.
Okay, so the goal is to assess and optimize the performance of several different high-resolution global and regional models and simulating a single MJO event during the 2009 year of tropical convection. And questions we want to address is how does model performance change as we go from grid spacings of 50 kilometers to 5 kilometers. So the idea is presumably, this has to be tested, that you're going to get an MJO at some point when you go to fine enough resolution, and then why is your model performance changing as you go through resolution? What is missing at the low resolution? And then how does performance at a given horizontal resolution depend on model physics? For example, parameterization of convection and microphysics. So this is a collaborative effort among several different research centers, and we're using 4 different models. So I'm using the WRF ARW, which can be run globally or regionally, and current plan is to run sort of a regional domain like the 45 south to 45 north, where you're just simulating the tropics. Julio Bacmeister is an expert in using CAM5 at high resolution. Bill Putman has been running GEOS5 at high resolution, and Ming Zhao has been running HiRAM. So all these investigators will be running these models on a certain case. And just to show you that already these models are being run at fairly high resolution and making very beautiful pictures that you can compare with observations, and sort of at glance say these models look virtually very similar to observations. So the top panel here is a GEOS5 simulation of cloudiness at 5 kilometer resolution, and the bottom panel is a GOES observed cloudiness picture. So the case we're looking at is from the 2009 year of tropical convection case. So the MJO, in terms of an index that's become popular, sort of develops around October 25th, and it's a canonical event in that it progresses across the Indian Ocean through the maritime continent and the West Pacific, and this is sort of a diagram just showing that it's a good case to look at very high amplitude. And also these tracks here are some tropical storms that developed in this case, so you can ask, is your model able to capture these storms at lead times of, say, 10 to 15 days? So the current project status, we're spinning up. Right now, we're waiting to get accounts on Gaia, so that's actually been more difficult than expected, but we're getting close. And soon we will be using Gaia's huge computing resources to do some of these simulations. And so I'm going to turn the talk over to Julio at this point.
Okay. Yeah, hello. I'm going to talk about some preliminary results from CAM5 at high resolution, and by that, in this global context, we mean quarter degree or around 25 kilometers. So first I'll just show briefly some tropical cyclone results. As Stefan mentioned, these models are able to get tropical cyclones. Of course, one of the uncertainties as we go to these resolutions in global models is how to parameterize convection. So I'll show a sensitivity, the sensitivity of the simulation to removing our convection parameterization. And finally, I'll talk about condensate loading, which is a detail that I think is important in itself, but also suggests the importance for global models of doing a better job of simulating precipitation microphysics. So first I'll quickly show some TC number, tropical cyclone numbers and tracks from CAM5. I'm showing results from one season here, and I'll just say in words that we get a good contrast between active Atlantic seasons and quiet Atlantic seasons, 2005 and 2006 in this case, and long runs with Cam 5 physics just completed by collaborators at Lawrence Berkeley show that we get very good statistics from Cam 5 at 25 kilometer resolution for longer periods from 1979 to 1997. So I think it's safe to put CAM in the category of global models that do a reasonable job of simulating tropical cyclone climatologies simply forced with observed SSTs. So this shows 3 ensemble members from CAM. This is a standard model compared with the international best tracks climatology for, I don't remember what the acronym stands for. It's an observation of climate, of cyclone tracks, tropical cyclone tracks for the last 150 years or so. And the point of this plot is just to show that the model is doing a reasonable job of capturing the main features of the tropical cyclone climatology in northern summer. This is a diagnostic time and hours spent at particular categories in Cam 5. Our tracking algorithm has trouble detecting weak tropical disturbances, but you see as the category increases, you see a tendency, I think, for the model to maybe overestimate the intensification of tropical storms. Even though, as you saw before, it seems to be getting the numbers at least approximately correct. Several global modeling groups have found that the deep convection scheme plays a critical role in their simulations of tropical cyclone climatology, and I haven't shown it here. It's also true that when we look at CAM precipitation, the precipitation in tropical cyclone cores is completely dominated by large-scale precip. So it's a natural question to ask at these resolutions: what happens in these simulations if we just simply remove the deep scheme? In CAM, this would be the Jean-McFarland scheme. So what I'm showing here is a quick plot of, again, this is one of our ensembles from the standard CAM on top, and in the bottom is the same period run without the Jean-McFarland scheme turned on. What you see is that the number of cyclones, especially in the Atlantic, has gone way up, and you probably can't remember the track plot from observations, but this is clearly a large overestimate in the number of storms forming during this season. If you look at the time hours spent diagnostic, the red shows the result from the run without convection, without the deep convection scheme turned on. Black, I forgot to mention before, is the observations. And you see that in all categories, when we turn off the convection scheme, the model is generating lots of activity, much more activity than is actually observed. This shows a PDF of probability density function, or a frequency distribution of precipitation intensity from the standard Cam 5 in black, our simulation with the deep scheme turned off, and the trim 3B42 observations, which are at about 25 kilometers squared also. It compares the intensity distribution in these things, and what you see is that with the deep scheme off, the high intensity precip events, which were already sort of overdone in the standard CAM, are even more so. Interestingly here, we show the contribution of convective precipitation to the total, and you can see that at these very extreme events in CAM, almost all of the precipitation is coming from the large scale. Okay, so now quickly I want to try to go through an argument for the importance of condensate loading even at these scales. Now, condensate loading simply refers to the weight of precipitating condensate, mostly because that's the largest fraction of condensate, but it refers to the weight of condensate in the pressure field of the atmosphere. This shows results from a WRF simulation. This is a fully non-hydrostatic 500 meter simulation with 15-minute output, and what it shows is the pressure generated from condensate, all condensate, that is liquid, cloud liquid, cloud ice, rain, snow, and graupel. So this is the surface precipitation on the horizontal and the surface pressure signature of the condensate as a function of surface precipitation. So what you see is that at intensities of 1,000 millimeters a day, which is very intense, but does happen in the model, we're getting surface pressure signatures of around three or so hectopascals or 3 millibars. In the tropics, this is a significant pressure perturbation. So what the white lines show are sort of a linearized parameterization of this effect, which we have implemented in CAM. It's a fully three-dimensional pressure field that varies as a function of surface precipitation. When we put that into CAM, our precipitation intensity distribution is reduced at the intense rates with the parameterized loading. You see it here in the green, and you see it's really it's very selectively cut back on the frequency of intense events in the model. This shows another frequency distribution. This is, in this case, it's of vertical motion at 150 millibars, and the CAM control is shown in black here. And you see that without the loading, the model produces a large number of very intense events of very intense upward motion, which is significantly reduced with this precip loading. So I want to point out, as I said at the beginning, this I think it's an important aspect of the atmospheric mass field that has to be included in CAM at these resolutions. But the point I want to emphasize here is that re-evaporation of precipitation can multiply this effect simply through evaporative cooling by a factor of about 8. So I think the apparent importance of this effect in the high-resolution simulation suggests that we really need to worry about precipitation microphysics in global models at these resolutions. So I'll just close with one more slide showing that this parameterized precipitation pressure loading has an effect even in the annual mean precipitation. The plot shows annual mean precipitation in the Pacific. South America and North America are over on the right side of the plot, and here's Australia. This band of precipitation, the intertropical convergence zone, is too intense in the standard CAM, and you see that the intensity of precipitation in the ITCZ has come down quite a bit in the run with loading. You also see there's less of a tendency for the model to split the ITCZ in the north from that in the south. This is a common problem in climate models that becomes exacerbated when you couple them to an ocean. So it looks like the condensate loading is having an effect both on the high frequency intensity statistics of precipitation and also on the seasonal or the annual mean precipitation in the model. So this is again, this is just an indication of the importance that precipitation microphysics is likely to have at these resolutions. This condensate loading effect is something that's been present in mesoscale models. I think it is present in mesoscale models, and it's present. Its effects in those models will be. There still may be an unaccounted for effect in those models that is related to the amount of precipitation in those models that's coming from the convective parameterization, which does not, which wouldn't enter into this. So I'll just close by saying that I think this is one of the things we're keeping in mind in this project, this sort of need for better precipitation dynamics, and I'll just leave it there.
Great, thank you, Julio and Stefan. So we've arrived at almost 2 o'clock now, which is the formal ending of the webinar. However, I believe the speakers are able to hang around for another 15 minutes or so, and we have the phone line and the WebEx, and we do want to have a discussion session. So feel free to log off or leave the room if if you're not able to stay past 2. But otherwise, we'd like to have some question-answer discussion right now. Before you do log off, if anybody is leaving by 2, I'd like to remind you that the next MAP webinar is coming up on December 13th. It'll start at 1 o'clock, just like this one, and it's on the topic of Madden-Julian oscillation variability and prediction. So we got a nice primer on that today from Stefan and Julio. So without further ado, I'd like to open it up to the phone lines or anybody in the room here if there are any questions for any of the 3 speakers or general observations. Also, if the speakers have questions for each other.
This is Yolande Sarah. Can you hear me?
Yeah, we can hear you.
Okay, great. I had a comment for Brian Colle. We've been looking at tropical storms, so it was very interesting to hear your talk. I thought that was a great talk, and we also used Kevin Hodges' tracking. And I've been using the WRF, tracking the tropical waves, trying to look at, sort of like you, we're going to be looking at the storm track in the future as well, and so we're in the process of understanding the current century runs. And what I'm finding is that you didn't mention anything about spectral nudging, and I noticed that you're showing from the NARCAP runs that the WRF and I believe one other CRCM model wasn't capturing as many centers as you expected or what you saw in the data. And what I find is that the WRF being forced with ERA interim, it won't capture them without some nudging of some sort. And we've tried various mild nudging. We need at least about 1,000 kilometers, 1,200 kilometer nudging and above. So wavelengths of about 1,200 kilometers and above the boundary layer in order for the model to actually propagate the waves across the domain in the Inter-America Sea. And I wondered if you had considered using nudging or what, because I know NARCAP, I'm pretty sure only like 1 or 2 of those runs used it.
Yeah, I mean, that topic has come up, and we may be heading that direction. Okay. Yeah, I guess the first step was just kind of see what the NARCAP can do and what we can do in kind of a standard approach.
Right.
And obviously you're doing the tropics, right? You said.
Yeah.
And so, I guess in the mid latitudes, you know, it's a question of it's obviously a different environment, and the question is with can these regional models propagate these disturbances? We're talking about upper level PV anomalies or short waves in a realistic way without, you know, getting destroyed or with certain model biases and so forth. So my hope was that it was actually I would say a simpler problem in mid latitudes, but the question is whether it can generate a realistic climatology of these upper level disturbances that are more baroclinic in nature. Yeah, and then seeing what we can do from there before doing the nudging. But you're right. I mean, if we find there's a bias or a persistent problem, we're going to likely have to try something.
Yeah.
This is Ray Arritt. I'd just like to make a comment as a NARCAP participant that in the NARCAP ensemble, the CRCM and the Scripps model were the 2 that used spectral nudging. So it might be a helpful comparison for you to look at those 2 models compared to the other 4. Because again, we're in this region near the outflow boundary where non-nudged models tend to do quite poorly.
Yeah, thanks, Ray. That was a CRCM. What was the other one?
It was the Scripps model, which for whatever reason is usually given the symbol ECP2 or something like that.
Okay. Thank you.
Hello, this is Paul Diermeyer. I have a question for Ray, actually 2 questions. I enjoyed your presentation, but I wasn't quite clear, the statistical downscaling that you showed. First of all, was that applied sort of as a general bias correction, or was it also being applied to improve the simulation of anomalies in certain cases? And then kind of extending on that, is there any plan to benchmark the various dynamical downscaling models using the simple statistical approach as sort of a minimum hurdle to clear?
Yeah, if I understand your first question, the statistical processing that Ruby did was on the results, and it wasn't something like removing biases from the CFS before the downscaling was done. I may be misinterpreting the question there. With regard to the second question, Dennis Lettenmeyer is doing the statistical downscaling for the project. We don't yet have that to compare to, but it's obviously something that we want to look at to determine whether this whole, all the work that's been done network downscaling is really worth the effort.
Okay, thank you.
Are there any other questions on the phone line? All right, if there are no more questions, I think we'll call an end to the webinar. I'd like to thank our speakers for 3 really outstanding presentations, and for everybody listening in. Until next month, we'll see you on December 13th. Thanks.
Thank you.
Thank you.
Thank you.
Thanks.